All right, so last time we introduced some constructions of local endoscopy for quasi-split groups. So let's do a short overview of the different things we did. So for G connected reductive group, the first thing we considered was stable conjugacy. And one of the things we showed is that when we have a strongly regular semisimple element, then the rational classes in the stable class of that element, we introduced what it means, what the stable class was, and rational class simply means GF conjugacy class in that set, which is the stable class. That was in one-to-one correspondence with the kernel of the following map on Galois cohomology, where here T is the centralizer of delta. And this was this bijection here. So an element delta prime in here representing the corresponding rational class would be sent by this bijection to a cohomology class called the invariant of delta and delta prime that was explicitly defined last time. And then the next thing we discussed was endoscopic triples, H, S, eta, where we said what those things were. In particular, this element S was essentially a central element in the dual group of H, whose coset modulo the center of G hat was Galois fixed, and moreover, this element is liftable to a Galois fixed element in the center of H hat, but the notion, the datum of the lift was not recorded. Just the possibility of lift was there. And then we discussed admissible embeddings of maximal tori of H into G, and that concept gave us the notion of related elements. Initially they're defined over F bar, but you may ask for them to be defined over F if you so like. And then related elements, gamma in H, gamma in H, and delta in G. This is also a purely F bar notion, but you can again ask for these elements to be defined over F, if you like. And then when you have two related elements, they give, if they're strongly regular semisimple, they gave rise to a unique isomorphism between their centralizers, for which we gave a name like this. So those were the different concepts for a general connected reductive group. And then in the particular case where G was quasi-split, we introduced further things. One was the transfer factor. So for this, we're going to fix what we called last time extended endoscopic triple. Which was an endoscopic triple together with an extension of this eta. If you remember, eta was an embedding of H hat into G hat, and it can be, we can choose an extension, if we're lucky, for it to exist, to an embedding of L groups from LH into LG. And then a transfer factor. So that was a function. It was a complex valued function that takes two variables. One is a strongly regular semisimple element of H, and another one is in G. And it depends here on a Whitaker datum, which is a notion we also introduced last time. In the notes, I'm going to put explicitly how one constructs these transfer factors. Unfortunately, it takes a little bit of time to say all these things, so I won't have time to do it in the lecture. And then we defined the notion of matching functions. And that was defined by matching of orbital integrals, namely two functions fh and f, one on g and one on h, are matching if the stable orbital integral of fh at an element gamma is related in the following way to the orbital integrals of f. The notion of transfer factor is, of course, used here in the definition of matching functions. And then finally, we had the spectral side of endoscopy, and I kind of rushed through it, so I want to say it more carefully now. It is the following. So it is the following conjecture, which encompasses the local Langlands conjecture. So let phi from LF to LG be a tempered parameter. I'm using here Arthur's notation for the so-called local Langlands group. So this is simply the Weil or Weil-Deligne group, depending on whether, well, let me not leave out C as a possibility. So this is the Weil group if F is Archimedean, or the Weil-Deligne group if F is non-Archimedean, and or you can also put here a local function field if you like. So let's take a tempered parameter. So what should happen? There exists an L packet pi phi g, which means a finite set of tempered representations corresponding to this parameter phi. There exists a map from this finite set pi phi to the set of irreducible representations of a certain finite group. Which finite group is it? So we can first take the centralizer of the parameter. This is my shorthand notation for the image of the parameter in G hat, in LG, really. And so I can divide out from this centralizer the Galois fixed points in the center of the dual group, which will always centralize anything. So they're certainly in here. And then I can take the group of connected components of this. So this will be a finite group. And this is the group whose irreducible representations I'm taking. So I'd like to have such a map which is injective when F is over R, and bijective when F is over QP. So that would be a parametrization of this set by this set of representations. Furthermore, there exists a unique generic representation. We have fixed a Whitaker datum, and we've used it to normalize things on the geometric side, namely the transfer factors. It also has influence on the spectral side by saying that there is a unique W generic representation in this L packet. This is Shahidi's conjecture. And moreover, this map here is supposed to be normalized in such a way that, so let me give it a name. There exists a unique double generic representation, maybe pi sub W in here. And this pi sub W is mapped to the trivial representation here. Okay. And then finally, assume that this tempered parameter came from an endoscopic datum. In other words, the tempered parameter looks like this, but actually it came as a composition of a parameter for the endoscopic datum with this map L eta that is part of the extended endoscopic triple. If we're in that situation, then what happens automatically? The endoscopic element S lies in the centralizer of this parameter, just by construction. And if F and FH match, according to this definition up there, then the following character identity should hold. If I take the sum of the members of the packet here, this is the identity I wrote down last time, but now it can be explained more carefully what it means. What does this here mean? This means the trace of rho at S, where rho where pi corresponds to rho under this map over there. Rho is a representation of the script S phi, which is a quotient of the usual S phi, so we can feed it the element S in S phi in it. We can evaluate its trace. Okay, so this virtual character on G is supposed to equal to a similar virtual character on H. In fact, here I may actually substitute this for the element 1 and it's not going to make a difference, because the element S for H is central. I don't know if I recall this. The element S is central for H, and when we divide out by the center for H, it's going to go away. So, but it's more symmetric if you put the S in here, just for aesthetic reasons, if you like. Okay. Now, there is a minor subtlety here. This pairing depends on the Whitaker datum because this bijection here, or injection, depends on the Whitaker datum. So what's here with the Whitaker datum? Well, it turns out, it's not difficult to show that because this S is actually central and we're really putting the element 1 here, which means we're actually computing the dimension of this representation. Well, the way this behaves under changing the Whitaker datum, this representation is by tensoring by a character, so its dimension is unchanged. Even its traces would actually change. And since we're only computing dimensions here, it doesn't matter which. We just pick an arbitrary Whitaker datum and it's well defined. So this was the quasi-split story. And so what we want to move on now to is G not quasi-split. This is what we want to discuss today. And so, let me remind you of the concept of an inner form. It already occurred last time. So, in a form, an inner twist is an isomorphism between, so two groups G and H are inner forms of each other if there exists an isomorphism over F bar with the property that this isomorphism, it may not be defined over F, but it differs from its Galois conjugates by inner automorphisms. Okay. And so, being an inner form is an equivalence relation. And the equivalence classes in this equivalence relation are called inner classes. And so, it was a fundamental idea of Adams, Barbash, and Vaughan that you shouldn't just treat individual reductive groups, you should treat entire inner classes. treat entire inner classes together. So let me give you a very basic example. And really, the thing that can start you thinking about the fact that something may not be quite right is this adjective here. The fact that you have, in general, only an injection from the L packet to the set of irreducible representation of the centralizer. When you have a p-adic group, you don't quite see this, but you see other issues. But when you have a real group, already in the quasi-split case, you see something is very strange. And I think Schellstadt, who worked out most of the theory, or really all of the theory for real groups, was bothered by this, and she called the elements in here that are not in the image ghosts. Probably she found them spooky, and they are spooky. Why are they there? They're not supposed to be there. Well, they do something, but in order to see what they do, you should look at other inner forms. So the example is unitary groups. Over R. Okay, so let's look at UPQ. So this is what the unitary group looks like over R. It has a signature P and Q. And so let's take phi. So first of all UPQs for P plus Q equals N are inner to each other. Here N is fixed, and P and Q vary with P plus Q equal N. All of these constitute an inner class. Okay, so let's take phi discrete parameter. Then what you can see is that the size of the L packet for UPQ for any discrete parameter is the binomial coefficient N over P, or N over Q. On the other hand, the size of this group script S phi, which is an abelian group, so its size will be equal to the size of its irreducible representations, this is 2 to the n minus 1. So there seems to be some serious mismatch between, this side and that side. However, you're going to notice this formula, which somehow suggests that if you take the disjoint union of all the L packets, you get much closer to this number. Well, how is this number related to that number? Okay, that's easy. You take this number and you multiply by 2. But this is the size of this group where you do not divide out the center. And there is a good reason for that. So this is going to be our guiding numerical incident. For now, incident. Later we'll see that it's actually theory. Okay, so now the first question is, okay, if we are to embrace this idea of Adams, Barabash, and Vaughan of treating inner forms together, we have to find a way to say, when do we think of two inner forms as being the same, and when do we think of them as being different? In other words, we need to come up with the concept of an isomorphism of inner forms, and then we're going to treat isomorphism classes of inner forms. We're going to say two isomorphic inner forms for us are the same. We'll treat them together. So, need the concept of isomorphism of inner forms. And it has to have a certain property. So we want, what is it that we want? We have the following condition on the concept of an isomorphism. So the set or group of automorphisms of an inner form G prime, if you like, has to preserve conjugacy classes and representations of the F points. After all, we're interested in invariant harmonic analysis on the group G prime of F, an inner form of G. And so we would like whatever notion of isomorphism we create, the resulting notion of automorphism should preserve conjugacy classes and representations. Okay, so let's start building up. The simplest thing you can do, is G prime, G double prime, inner forms of G are isomorphic if and only if G prime isomorphic to G double prime as reductive groups. Why not? This is the most naive thing you can ask for. Is that a good thing? And how? So here is an exercise. One, now, remember by my letter psi here. So psi, so given psi from G to G prime, we have psi inverse sigma psi. What is that thing? Well, that is a cocycle for the Galois group acting on G adjoint. Okay? Well, the class actually depends on psi. But its image in H1 Galois of the all automorphisms of G, that thing does not depend on psi. That depends only on G prime, the inner form. So depends only on G prime. So we get a bijection between isomorphism classes of G prime, inner forms of G, up to this notion of isomorphism, just isomorphic as algebraic groups, with the image of H1 Galois G add to H1 Galois automorphisms of G. And then 2, the automorphism group of G prime under this notion of is literally, okay, I have a conflicting notation here. So on this side, I mean under this concept of isomorphisms, the automorphism of an inner form. But of course, isomorphisms for me are just isomorphisms of algebraic groups. I've kind of ignored the inner twisting. Well, these are just the F points of the automorphism group of G prime. Now that's obviously bad. This is bad. For example, transpose inverse on GLN does not preserve conjugacy classes or representations. Namely, it sends every representation to its contragradient. So it fails our condition here. Okay, let's look at the next possible concept of isomorphisms. So next thing, the next thing we can do is now say, introduce a concept of isomorphisms of inner twists. So let's say we have 2 inner twists, psi1 and psi2. What is going to be an isomorphism between them? An isomorphism is a pair F no, not yet. An isomorphism is just an isomorphism over F between G1 and G2, just like before, but it has to now satisfy an extra condition that takes into account the twisting, such that, so this is going to go here, F, such that psi1 composed with F composed with psi2 inverse is an inner automorphism. Okay, so we've now made the notion of isomorphism stricter. You have now exercise psi comma G mapping to psi inverse times sigma psi is a bijection between isomorphism classes of inner twists and H1 Galois G add, which is different from the image of it in here. And moreover, then 2 is the automorphisms of psi G prime are now the F points in the adjoint group of G prime, which is, we can also write suggestively like this. So this classifies isomorphism classes, this classifies automorphisms within each class. Okay, now clearly this is better because it disallows outer automorphisms. It only allows inner automorphisms. So on the surface of it, it looks better, but there is a subtle point here, which is there is a difference between the notion of outerness for an automorphism when you think of it as, when you think of the algebraic group and when you think of the topological group you get by the taking the F points of an algebraic group. And so even though you disallowed outer automorphisms of algebraic groups, what you did not disallow is outer automorphisms of the F points. So the example here is PGO2 of R acting on SL2 of R. And here we have 1 minus 1, and this switches holomorphic and anti-holomorphic discrete series. We don't like that. Bad. And so this is also a problem. Okay, so that concept of isomorphism of twists was better, but not sufficiently good. So then Vaughan finally suggested something that actually alleviates the problem, and that's the concept of a pure inner twist, which is going to be a triple G prime psi and Z, where psi is going to be an inner twist, and Z is going to be a Galois one cocycle in G and not in G add, such that psi inverse sigma psi is the inner automorphism given by this conjugation by this particular cocycle. Okay, and so now we have the next exercise, which is that taking triples, G prime, psi, and Z, and mapping them to the class of Z is a bijection. Oh, I did not tell you what then the concept of an isomorphism is. So let me do that first. The whole point of introducing these things is to make to find the right notion of an isomorphism. So an isomorphism between two such things consists of an isomorphism over F between G1 and G2 and an element G in G of F bar with the following property, where remember, what did we do here? We said this one was supposed to be inner. Well, now it's not just inner, but it's affected by this G. But moreover, at the same time, and I always get the inverses confused, so I'm going to copy it from my notes, this G also translates in the right way the two co-cycles here. Okay. And so now comes the exercise, which is 1, if you take G prime, psi, and Z and map it to the class of Z, this is an isomorphism, or sorry, let's say a bijection between isomorphism classes of pure inner twists and H1 Galois G, and by analogy with the previous exercise, you can imagine now what the automorphisms are going to be of a pure inner twist. So the automorphisms of a pure inner twist are now the f points of G prime. And indeed, conjugation by an f point in G prime is obviously an inner automorphism for the topological group G prime F, so it's going to preserve conjugacy classes and representations. So finally, we've arrived at a point where we have a good notion of an isomorphism of inner forms, and in order to get it, we had to endow the inner form with some additional data and require the isomorphism to preserve that additional data. Okay, so there is a serious problem here. Which is that usually the map from the Galois cohomology of G to the Galois cohomology of the adjoint group is not surjective. So not all inner forms can be purified. Okay. Now, let me ignore this problem for a while and let me tell you, if you're dealing with inner forms that can be purified, why does this notion resolve all the problems that, or I didn't even tell you what the problems are if you try to brute force the inner form case because of lack of time, but there is a nice list of problems. Let me just tell you how one proceeds with the theory once this notion has been established. And then after that, I'll tell you what to do with the problem here. Okay, so for now, we're going to discuss endoscopy for pure inner forms. Yes? Yes? F. F. This has to be an isomorphism of F groups. Right, so psi, these fellows here are isomorphisms over F bar. This fellow is isomorphism over F. All right. Well, I can just maybe verbally tell you what the problems would have been had you tried to brute force your way through a non-quasi-split group with endoscopy. First of all, you wouldn't know how to normalize a transfer factor because there is no Whitaker datum which was used in the normalization. You can come up with a way to construct a transfer factor, but it would be only well-defined up to a constant. And so you'd have to wonder, well, what's the meaning of the character identities if the transfer factor is only well-defined up to a constant? You can try and say, well, I would be happy if my character identity is satisfied up to a constant too. But then it turns out that in this bijection between an L packet and irreducible representation of the centralizer, the two sites are so far off of each other already for the group SL2 that there is no way to make a character identity true even up to a constant. So things end up being off both on the geometric and on the spectral side. You can then, of course, say, okay, I'll make the character identity even weaker, where I don't want the universal constant, but I'll just put a constant in front of each representation. Then, of course, you can have a character identity, but then you have so many constants floating around whose relationship you're not so sure what it is that you can't proceed with the theory neither locally nor globally. So you end up getting stuck because when you try to use a trace formula, there's so many terms that float around that if you don't have the local constants pinned down perfectly, you cannot hope to make cancellations in the formula. So you end up in trouble. So here is how you proceed once you have the notion of pure inner forms. So you're going to introduce the concept of an element and a representation of a pure inner twist. So element of a pure inner twist. Well, it's going to be a pure inner twist together with an element of it. So nothing terribly exciting. So it's going to be a quadruple where G prime psi Z is a pure inner twist. And gamma, or actually I wanted to call these fellows delta now. Delta prime, is an element in here. And then two such elements, then the question is, what is rational conjugacy? We're going to extend the concept of two elements being rationally conjugate from two elements in the same group to two elements in different groups. That may sound a little crazy, but we're going to say G1, psi1, Z1, delta 1 is rationally conjugate to G2, psi2, Z2, delta 2 if there exists an isomorphism Fg from the one to the other. So this is G1, psi1, Z1, G2, psi2, Z2. This is the concept of isomorphism we introduced over here. Mapping delta 1 to delta 2. So that would be the concept of rational conjugacy. And then there is a corresponding concept for representations. So a representation of a pure inner twist is going to be a datum like this. Pi, you can fill in the blanks if you like. This is a pure inner twist. This is a representation of the F points of G prime. And two such will be equivalent. So G1, psi1, Z1, pi1, equivalent to G2, psi2, Z2, pi2. Definition is the same as up here. There has to exist an isomorphism between the pure inner twists, sending the one representation to the other. What is what? F comma G? Is that the question? It's this. It's an isomorphism from the one pure inner twist. The tuple F comma G is an isomorphism from the one pure inner twist to the other. So if exists isomorphism F comma G from the one to the other pure inner twist, sending the one representation to the other. Pi2 is pi1 composed with F. All right. Another exercise. Let me tell you what stable conjugacy is. No, for now I'm not assuming anything, but I'll start assuming G is quasi-split in a moment. So far, all of these things work for any G. All right, maybe I should say that 5 two such things, G1, Gi, Xi I, Zi, delta I, are stably conjugate if Xi1 inverse delta 1 and Xi2 inverse delta 2 are conjugate in G of F bar. All right, I can pull these back to G. They both will be now F bar points. I can still ask them to be conjugate in G of F bar. Okay, and now comes an exercise. So see, what we're doing now is we're really putting flesh on the idea of treating all inner forms together. So we're saying, well, we're going to treat all elements of all inner forms at the same time. So we're going to have this notion of an element of an inner form which has the inner form and the element in there, and we're going to look at all possible inner forms and all possible elements all at once. And we're going to introduce the notion of conjugacy of such elements which spans across inner forms. That's this notion. And also the notion of stable conjugacy, which also spans across all possible inner forms. And the same with representations. And so now we have the following exercise. The set, oops, that's not how you write set. The set of rational classes, rational with respect to this definition 2, in the stable class of delta in G of F strongly regular is in bijection with H1 gamma T. Notice there is no kernel anymore. It's just the entire H1 gamma T. Why is there no kernel? Because there is a natural map to H1 gamma G, and the image of the element is going to tell you exactly the class of this element Z in the form in which this element lives. Huh. Yeah? No, but I've been using this strong irregular all the time. So I'm talking only about strong irregular elements for now. Of course, you can generalize this using the same kind of Kottwitz idea that I introduced last time. I just don't want to discuss this because that would take even more time. How does this bijection work? So bijection is as follows. Okay. If G1, Psi1, Z1, delta 1 is stably, is stably conjugate to G identity 1 delta. This is the trivial pure inner twist. So there exists a G2, Psi2, Z2, delta 2 conjugate to G1, Psi1, Z1, delta 1, such that psi of delta is equal to delta 1. Define the invariant of delta delta 1 to be the class of this Z2. There is a 1 here, and this is a comma. Okay, so now we have a concept of a cohomological invariant for two elements that are stably conjugate but live in different groups. And that cohomological invariant lives in this finite abelian group, and in fact it exhausts the entire finite abelian group by going through all the different rational classes inside the stable class. And so now, with this, we can now define a transfer factor say again? So yes, so let now H, S, L eta be a extended endoscopic triple for, okay, so now I'm going to fix a quasi-split group. Now, part of the theory of reductive group says in every inner class there is a unique quasi-split form. Since we're treating an entire inner class, I'm now going to fix the quasi-split form and treat all of its inner forms together. So fix G0 quasi-split. Okay. Let's take an endoscopic triple for G0 and let W be a Whitaker datum for G0. Now what we're going to get a transfer factor delta W from H F strong irregular times G F strong irregular for any pure inner twist G psi Z. This is what we wanted. We wanted to treat groups that are not necessarily quasi-split. G is one of them. We realize it is a pure inner twist of a quasi-split G0. If we so can, it's always an inner form of G0, but it may or may not be purifiable. Let's imagine that it is. So we're avoiding the big problem. We're avoiding the serious problem here by just ignoring it, which is oftentimes a good strategy. And then here is the definition. First of all, there is a theorem, or a proposition, or a fact, or however you want to call it. There exists a delta 0 in G0 of F, strongly regular, stably conjugate to this element, G psi Z delta. To which element? For any delta in G of F strongly regular. This is due to a theorem of Steinberg, which you can apply and you get this proposition. And then you have the following definition. You define the transfer factor, gamma delta, to be the transfer factor for gamma delta 0 that we defined for the quasi-split group last time, times the invariant between delta 0 and delta that we now defined here, paired with, again, the same thing, gamma delta 0 hat inverse S. Okay, so this is a definition of a transfer factor, but it had to include this invariant, and notice that this invariant used this purifying data for the inner forms, and without them you would not have been able to measure invariance between different elements in different groups. This is where all this comes from. Okay, now there is a little wrinkle here, which is what? Well, let's remember what this thing was. So this really lives in pi 0 t hat modulo zg hat. I need more parentheses. This is where this endoscopic element lives, by definition. Okay, on the other hand, where does this element live? This element lives in H1 gamma t. Now, in the quasi-split case, we argued as follows. We had the torus in the simply connected cover, and we argued that the invariant in the quasi-split case lifted to there. Whereas on the other hand, we have here the natural map from pi 0 t hat gamma. And we knew that the endoscopic element is liftable to this. And so the fact that we have something liftable here and something liftable here told us that there is a canonical pairing between the two. Now what happens is, this invariant is no longer liftable to here. because it's an invariant that measures relative position of elements in different groups. And so you cannot lift this to here. And so the fact that you could lift your element S to here is of no use. What you actually need is an element down here that you can pair with Tate-Nakayama duality. You really need the element here, and two different lifts would give you two different results. And so you need to refine your concept of endoscopic data. So definition, a refined, and there's different ways to refine things. So let's call it a pure refined endoscopic datum is a datum where you just lift the S to an S dot, where HS eta is as before. And I guess I used triple, sorry, triple, and S dot in here lifts S. And in that situation, but the point is now, because you have defined this refinement, you need to also define an isomorphism of such things. Let me not write it down, I'll just say verbally, you require the isomorphism to preserve the lifts. If you have two such things with fixed lifts, you want the isomorphism to preserve the lifts. So you get a finer notion of isomorphism, and this should remind you of the finer notion of isomorphism of inner forms that we introduced. So all of these things are related. And then we have a conjecture. We can now refine the conjecture. So let phi from LF to LG0 be a tempered parameter. And let's such that, so there, well, okay. So the first thing is, one, there exists an L packet, pi phi, we can call it a compound of representations of pure inner forms. That is, this set consists of such quadruples of things that we defined earlier, representations of pure inner forms, of course up to equivalence, so equivalence classes of representations of pure inner forms. Two, there is a bijection of pi phi with the set of irreducible representations of pi 0 S phi. And this is always a bijection, whether F is real or p-adic. This is just always on the nose. Notice we're not dividing out by the center anymore. I don't have a bar here, which was what the earlier group was. And this bijection has to fit in the following diagram. Here we have the base point map, which takes a quadruple of a pure inner twist and a representation and gives you the class of the pure inner twist. Here you have a central character, so Z, G hat, gamma, pi 0. Namely, Z, G hat, gamma, which we had divided out earlier, now sits in here, and any irreducible representation of this group is going to transform under a character by this central subgroup. So you can take this central character. And there is a map here due to Kottwitz. And you want this to commute. And moreover, we now are in position, say again, yes, thank you. This is G0. Thank you. Okay. And finally, we have the character identities. So in the situation where our parameter factors as before, okay, we're going to have the same kind of character identity, namely pi in pi phi G, pi S, theta pi F is equal to pi H, pi phi H, pi H, S, theta pi H, FH, where now F and FH match with respect to this here, this definition of a transfer factor, and this here is the trace of rho of S dot, where now rho is in here and matches pi. And this is all on the nose. So now I have 5 minutes to tell you what do you do with the serious problem that we wrote down here. Okay, I will do what I can. Say again? The serious problem was that not all inner forms can be made into a pure inner form. So what do you do? Well, solution to serious problem replace the cohomology, the usual Galois cohomology of G by a different kind of cohomology. We're going to replace Galois cohomology. What properties is this going to have? There will be an injection of the usual Galois cohomology into this new question mark cohomology. And the question mark cohomology is going to surject onto the cohomology of the adjoint group, which was exactly the failing of this set. That's the set that did not surject. This is 1. 2, there is Tate-Nakayama duality. For this Galois cohomology set, so that we can form such a pairing here that would allow us to extend the transfer factor. For this new question mark cohomology, there should be a version of Tate-Nakayama duality for this question mark cohomology 3. This should work uniformly for all local fields. 4, there should be a global analog with localization maps. So that once you have resolved your local problem at each place, once you have normalized everything canonically at each place, the canonical normalizations would fit together globally to give you the right global object. Okay? And, let's see, what is 58? So in the remaining 2 minutes, this is what I'll tell you about this. Okay, I think I'll stop here. I can say a lot. I can tell you so what is this question mark? You can define a certain profinite algebraic group as an inverse limit of restriction of scalars of roots of unity. So you take all finite Galois extensions and all natural numbers n. You take the algebraic group of nth roots of unity, you do a weight restriction of scalars, you divide out the diagonal copy, take the inverse limit. So this is profinite algebraic. And there is a canonical class in its second cohomology group. So H2 gamma PF rig canonically generated. So that leads to an extension because H2 classifies extensions of the local Galois group by this. And anything the local Galois group acts on, also this extension acts on. So you can consider the cohomology of this new profinite group, which is an extension of the Galois group, with values in this Galois module. And you can consider a subgroup of that, consisting of the so-called basic classes, where you look at cocycles of this in G0 whose restriction to this is central. And then it turns out that there is a Tate-Nakayama duality between this and the center. Well, the old Tate-Nakayama duality, or Kottwitz's map, related the usual Galois cohomology to something related to the center of the dual group. Here you're going to not take the dual group, but its universal cover as a Lie group. So if the group is semi-simple, its universal coverage is a simply connected cover. But if the group is a torus, its universal cover is affine space. And if the group is reductive, it's some kind of mixture between the two. And then you take the inverse image of the Galois fixed points. And then, well, no, contragonal. So this is the pairing. And so now I can state the exact same thing here. I can just say I'm going to replace this by that. And I'm going to put a plus here, which means the inverse image of S phi in this universal cover. And then I can run the entire machine as before. Now I can, so this property can be proved to hold. So any inner form can be purified using this cohomology. Using this Tate-Nakayama duality pairing, I can extend the transfer factor in exactly this fashion. Now I have a transfer factor for every inner form that I like. And now I come here and I say, well, there should be a compound L packet of representations of rigid inner forms, where rigid means I'm using cocycles not in Galois cohomology, but in this cohomology. There should be a bijection like this, and it should behave like this. And that's it. Sure. So UPQ does not have this problem. For UPQ, every inner form is pure, but for SL2, so H1 Galois SL2 is trivial. These are the pure inner forms. H1 Galois PGL2 is Z mod 2Z. So SL2 has a unique inner form, whose rational points are the norm one element in a quaternion algebra, the unique quaternion algebra of the local field. It cannot be purified, but it can be rigidified using this thing. And in fact, in this situation, this funky set here is also Z mod 2Z, and this map is a bijection. And this conjecture, by the way, by work of Shellstad, this conjecture holds in the real case. So you can just take Shellstad's work and sprinkle in the word rigid here and there, and then you're done.